All right, let's get going again. So now we're going to talk about reaction mechanisms. So how we construct them. I'll try to explain a little bit about flux and sensitivity analysis, and how we compare the predictions of the mechanisms with experiments. This is a long and complicated topic. I'll try my best to explain some things today. Please store up questions you can ask me, and I can explain more tomorrow about things. And I also say I've been working hard on this topic since 1993, something like that. So more than 20 years now. So there may be many things which are obvious to me that might not be so obvious to you, because I've been thinking about it for a really long time. So please slow me down and ask me questions, and I'll try to help you understand why, at least the way I think about it. You don't have to agree with me. All right, so there's several different ways that people try to construct reaction mechanisms, and they're based on fundamental philosophical differences. And so I'll try to explain this to you. It might not be obvious when you read a mechanism, because they usually don't specify their philosophy in the paper. But I'll try to explain that. And it's very important that you know this, what you're doing. So there's sort of for a long time, there was the popular approach was called the hierarchical approach. And there's still a lot of people who believe this as the way to go. And that was the dominant thing from the 80s until pretty recently, maybe 30 years. And I think that, in my opinion, it's not really right. And then the next approach that became very popular was the GRI mech type approach. And that one works for certain kinds of systems pretty well. And it worked for the methane. It was a very important system. But I think that has some problems too. And then I'll tell you what people actually do now, which is not neither of these approaches. And then there's a bunch of variants of what people do now, which are really different, depending on the philosophy. So there's sort of some models are made adjusted to fit, and some of them are made just predictive. Some are made by hand, some are made automatically. And all these methods, they all have problems, which is why no one method has taken over the field, and why different methods are used. So the popular approach, still now and for a long time in the past, was the concept is you wanted to just have a comprehensive list of every reaction and every species that could possibly be important in your model. And we'll take advantage of the fact that in combustion systems, it all comes down to hydrogen and oxygen at the end. And so we'll start from hydrogen and oxygen. And hydrogen and oxygen doesn't have any carbon in it, so we don't have to put any carbon species in our model. And so that makes it a lot simpler. So let's start with hydrogen and oxygen. That's the main idea. And then the idea was, after we really understand hydrogen and oxygen, now we'll stick in CO. And we'll learn all about carbon monoxide with hydrogen and oxygen. And then maybe we'll push it a little bit and we'll do formaldehyde. So we'll do CH2O, and with hydrogen and oxygen and CO. And then later we'll add methanol and see what that does. And we'll gradually work our way up to methane. And then maybe after methane we'll try ethane and ethylene. But then there's also ethanol and dimethyl ether and acetaldehyde. And then you start seeing that there's quite a few isomers with just 2 carbons and 1 oxygen. And of course, if you have 1 oxygen, you could have 2 oxygens too. So maybe there'll be ethyl hydroperoxy and ethyl peroxy and hydroperoxide and glycol and who knows. And it sort of gets out of hand. So this procedure has worked, is very sensible for hydrogen and oxygen, and then has kind of gotten into the C1s and the C2s, and I think it's sort of petered out as a current status. But I'll let you know about that. And the idea was that if you're just persistent enough, then you can do the next bigger molecules. So put the C3s in, and then the C4s, and the C5s, and the C6s. And eventually you're up to gasoline, and then you're up to jet fuel, and then you're up to diesel fuel, and keep going. Maybe we'll get to coal. Okay, so that's the idea. And ideally, the concept is you have like a hierarchy. So you have here's my hydrogen-oxygen mechanism. And so it has all the species you can make from hydrogen and oxygen and all the reactions that they can do and all the K of TP that are relevant to here. So here there'll be 20 K of TP because there's 20 reactions of the hydrogen-oxygen species. Okay? So the idea is you would nail them down so you would know those numbers. So those 20 numbers are totally fixed. And so now I add CO. And now I have a CO hydrogen-oxygen mechanism. And so now I have to add, I don't know, n more reactions, in all the reactions that what CO can do. So I'll get species like HCO and, I don't know, CO2. I'm not sure what other species. And then each of these guys reacting with all the species in here. And when I was working on this, I would do a whole bunch of experiments on carbon monoxide flames, carbon monoxide flow reactors, shock tubes with carbon monoxide. And with those, I would be able to figure out maybe there's, I don't know, 30 more reactions. And when I was adjusting the parameters in these guys to make them fit the data I saw in the carbon monoxide, I would leave these 20 fixed. That was the idea. And then next I could add in, formaldehyde. And then I would get some more, I don't know, 10 more reactions here. And I would hold all these 30 fixed and all these 20 fixed when I worked on these guys. So that was the idea of the hierarchical build. And hopefully you can keep building this up and you get to methane and ethane and just keep being bigger. And the key is whether at the first stage you could really nail down these 20. If you can nail them down so they're rock solid, then they're like we use the mass of the electron and the molecular weights of the elements and the Planck's constant. We use them as if they're like firmly known numbers. And we don't, when we're fitting our experiment, I don't try to readjust the value of Planck's constant to make my fit better, right? So yeah, that's what you want this to be. You want these to be so rock solid that you never have to adjust them again. Then it's like you're building a firm foundation and just building on it, building on it, building on it. And you don't have to go back and readjust the foundation because it's rock solid. But if I do it and I can't determine these 20, suppose I only determine 10 of them and there's 10 of them that are still uncertain, then when I get to this next stage, I don't know, should I be adjusting those 10 as well as these 30? Or what? Does this make sense? So the whole concept is based on the ability to nail down the first 20 and then the next ones and then the next ones and the next ones. And if we can do that, then this is a really good idea. This was originally proposed back in 1980s, 1981. Important paper by Westbrook and Dreyer. Dreyer's a professor here at Princeton. Westbrook's was the leader of the Lawrence Livermore combustion research program for a long time. And so that was a construction of comprehensive hierarchical chemical mechanisms. The other important word here is comprehensive. So the idea is that you're working on hydrogen and oxygen. You want to make sure you get all 20. You want to have all the reactions in there, all the species in there, all nailed down solid. And then when you add in CO, I'm going to make every single species I can make with CO react with hydrogen and oxygen, have them all in there, nail it down rock solid. And if you do that, then there's no gap for the next part of the mechanism to fall into. Does that make sense? It's like, that's the idea. And so people try to do this. And so there's a lot of papers in the early 2000s, around 2004, of hydrogen-oxygen mechanisms. And there's been a lot subsequent about this. So 2012 here, for example. See, 2004. And I'd say for hydrogen-oxygen, it mostly worked out, that they were able to nail down most of the rate coefficients pretty solidly. But it turned out that in the end, they had to use quantum chemistry to nail down a couple of the things. So it just didn't turn out that there was not enough independent experimental data that was possible to determine all those parameters. The 20 parameters is too many. And this gets back to there's an old saying about how with enough parameters you can fit an elephant. So if you have 20 free parameters, it's actually a lot. And so it's hard to avoid correlations between them. It's hard to nail them down unambiguously. So I think people thought in 1980s when they wrote that paper, I'm sure they thought that of course people would just go through and nail it on hydrogen and oxygen. And I think they were anticipating then immediately moving on towards methane and propane and butane and benzene and going right up the, but it didn't work out. And the real reason it didn't work out is there's just too many parameters. And at the time in the 80s, the quantum chemistry couldn't do anything. So they had nothing to help them. All they had was the experiments, and there was just not enough independent experimental data that could constrain all those parameters. So they're always left with guesses, approximation, something to deal with, to make it possible to get a fit. Or else you have, the embarrassing thing happened in 2004. There were, I think, 4 papers that were published almost simultaneously by 4 different groups, all with hydrogen-oxygen mechanisms, where the rate coefficients were different between all 4 of them. But they all fit all the data. Because the problem was there's too much flexibility with that many parameters. And so that's when then people called in quantum chemistry, started doing really fancy experiments to try to nail it down. And so I think by now it's kind of mostly nailed down, but it required the quantum chemistry to come in, which wasn't available until late 1990s, really. And then the problem is that as you go past hydrogen and oxygen, you have to add many additional rate coefficients as you go up to each of these different circles. And by the time you get to like C3 and C4, it's just completely out of hand, the number of possible species you have. If you consider all the radicals that you can make from every possible C4 species, combining with any number of oxygen atoms, it's like this a lot of species. And only maybe 3% of them have ever been observed. And so you have 96% of them are numbers where you have to estimate all the thermo data for all the species and all the reaction data for all the species. And so it's just not practical to be comprehensive. And particularly if you're trying to get it all from experiments. So there's actually quite a lot of experiments relative to data for hydrogen and oxygen, for methane. But as you get up to like the C4 species, there's many C4 isomers that no one has ever burned and measured anything about them. And so there's no data to fix it. And also, the concept here is that when you add a species, it only makes itself or a few other species, it doesn't make a whole lot extra. But in reality, when you get up to like acetylene, it's easy to get conditions where you have acetylene where it actually goes on and it makes benzene. And then once it makes benzene, it goes on and it makes naphthalene. And then who knows what it makes. And eventually you see soot. And so the number of species and the number of parameters goes completely haywire. And so what they did when they did this hierarchical approach is they very carefully restricted themselves to reaction conditions where no molecular weight growth would occur. So they could be sure they wouldn't have the things getting bigger and bigger. So that was fine. It helps you with constraints because it gets rid of a lot of possible species and a lot of possible reactions. But it also means you have to stick to certain temperature pressure regimes. And so you can never determine the rate coefficients at the other temperatures and pressures from this procedure. So you have like gaps all through your data. And it's just in general, it's just a bookkeeping issue also, that you just get so many isomers. It's just hard to be comprehensive if you're trying to do everything. Even, I'll show you later computer ways to do this, and it's possible to do it, but even with a computer, it's actually hard to enumerate all the things. And originally, they're doing this in the 80s, they're trying to do it by hand. It was just not possible. Now, at approximately the same time as the people working on the hierarchical method, another group started called GRI-MEC. And they were funded by the Gas Research Institute, and they wanted to have a good mechanism for methane. That was like a consortium of all the natural gas using industries. And so they could definitely need a natural gas model. So it was a pretty big collaboration. So all these different people were involved, and they wrote a really nice model for methane. And their philosophy was different. They started out by writing down a limited number of reactions that they were pretty sure were all the reactions that would be important for methane in certain conditions. And anywhere they found conditions where that would not be good enough, they just said, okay, we can't model those conditions. So they confine themselves to conditions where the chemistry is relatively simple, there would be no molecular weight growth, all the species would stay small, and so then they'd have a finite number of species and a finite number of reactions. But they didn't assume that we already nailed down hydrogen and oxygen. They said, let's treat all these reactions as being free parameters. And let's take all the data in the whole history of the world that has to do with methane or hydrogen or oxygen or CO or formaldehyde or methanol or any of these species, and let's put all that data into one gigantic data set, and then we'll do a gigantic least squares fit, basically, to vary all the parameters in our model and try to fit everything simultaneously. So this is the idea of being comprehensive in your data, that you're trying to not just have a comprehensive mechanism, but also comprehensively consider all the data. And it was informed by a Bayesian view. Do you guys know Bayesian? So they had the idea that you have some prior knowledge about everything, and then you're trying to use the data to refine your knowledge. And you get what's called a posteriori, after you include all the information, what your best estimates are. So they started with best estimates of all the rate coefficients and thermochemistry and everything. They had error bars on everything to start with. Some of the error bars were pretty big because it wasn't much known. And then they did this least squares fitting and tried to narrow the error bars and all the parameters as best they could. And sometimes the data let them narrow the error bars a lot, and some of the error bars they couldn't narrow at all because the data didn't really reflect, wasn't sensitive to some of those rate coefficients, and they would leave them. So this turned out to work pretty well. It was a huge step forward for the methane chemistry, and it's very widely used even today. This was a long time ago, they made this model. And this philosophy of trying to vary all the parameters within the error bars and use all the data is continued, and there's a thing called the PRIME project, and you can look up on the web. And you could join it if you want. And this is a project that tries to collect every data that might possibly be relevant to combustion. It has tools to try to do all the comparisons of the model to data, all the fitting procedures to try to get the best parameter values. And this whole project, when they worked on it, highlighted the need to try to maintain access to the raw data because they constantly had to refit everything because they were refitting, for example, hydrogen plus oxygen when they were working on methane within its error bars. And they wanted to go back to the original hydrogen oxygen data and make sure that they had everything consistent. And this is very helpful because they discovered actually that many of the assumptions in the original methane work were completely wrong. And the most important and interesting thing they discovered was that normally when you have a fuel, you might think that the fuel radical reacts with oxygen and burns up. That would be an obvious thing to think. But what they found out with methane is you make a lot of methyl radicals, but the methyl plus O2 reaction is actually, the equilibrium is back on this side at most combustion conditions. So except at very low temperatures, it doesn't react with the oxygen. And instead what happens is the methyl accumulates, it can't do anything. It accumulates and then it reacts this way. And the H can react with oxygen by the combustion reaction. And this one does some steps and gets to C2H3, and this one can also react with oxygen. And finally, you get to a C1 species. So this was like totally not known when they started this project. And they figured this out, and this is crucial for getting a reasonable mechanism for methane. It makes the kinetics very strange because it gets second order in radicals. So it's a kind of weird kinetics. But methane's weird. That's part of the reason why. So that was a huge hit. So all of a sudden we suddenly had a methane model that was like actually physically realistic, semi-quantitative, pretty close to experiment, fitted to everything that was known, consistent with everything that was known. So that was really a big step.
The fitted data, when you fit it, later when we apply the quantum chemistry calculation to find out the true values, then do they agree?
Not always, but usually within the error bar. So they also had error bars on all the parameters, and usually it's right. There was I think there's like one or two cases where there was something wrong with the experiment they were fitting to. And so then to fit it, they distorted some of the parameters away from the physical values. They didn't know it at the time, and then later people figured it out. And so there were several editions of the GRE mech. So I think the one that's out now is called version 3, and that one, there were some problems for sure in the earlier ones, especially GRE mech 1 is like you never see anymore. It's eradicated. It was wrong. And the prime, they actually just recently refit the whole methane data again recently in the prime project. So they're still working on this. And they also, okay, so previous people didn't understand the importance of having reversible reactions. And so a lot of the old models were done with irreversible. And it had to do with the solvers in the old days didn't have an easy way to do reversibility and enforce that K forward over K reverse had to be KC. But then these guys highlighted how important that was. So that was a really big advance too. But you see it has 325 reactions. That's a lot of parameters. So this is the problem with this gets to be a lot about data management. You need a heck of a lot of experimental data if you're going to nail down 325 rate coefficients. So most of their time was measuring stuff to try to get more data, mining all the existing data, trying to get all the raw data from all the groups that had measured it before, so they'd have every data to compare with. All right. And so this is like one example. So they would do sensitivity analysis on their model and find out which of the observables that they had data for were sensitive to which parameters. The ones that weren't sensitive, they just left out of the whole fitting procedure. And then they varied the ones that were sensitive to try to fit everything simultaneously. So for example, they decided that H plus O2 plus water vapor is a sensitive reaction to make HO2. So that's reaction number 35. And so that was an optimization variable in the GREMAC 3.0. And when they varied to fit everything, they had to change it by 20% from its value, which was well within the error bar known on that parameter before. So people accepted that. I don't know if this is really the true number. It's a number that gives, by varying a lot of parameters, gives a good fit. That doesn't violate anything I know. So it's believable. It's a believable number, but it's not necessarily the true number. And then they did all the work on them. And they tried to get every kind of data they could. So they did shock tubes, they had ignition delays, all kinds of combustion parameters, as well as individual rate coefficients, flame speeds, and mole fraction yields and flow reactors, and all kinds of stuff. So they tried every data. So a big part of their project was just getting the data of every possible thing that might depend on these reactions. Because if you have a model, it has the true rate coefficients in it, it's got to be consistent with everything. Because it's the same rate coefficient in it's a physical constant. So everywhere there's methyl radicals, they've got to be doing this reaction, methyl plus methyl, at the same rate coefficient. And if your model if you can't fit every experiment with that value of the rate coefficient, then something's wrong. That rate coefficient number is not right, and you have to do something. So that's why you have to find a lot of different data. And so there's a nice paper about this in the Proceedings of the Combustion Institute 2007 by Frank Locke, all talking about the philosophy of trying to do this. And then how important it is to get the entire scientific community involved in the data collection effort, because it's so important to get, if you're going to try to determine all the parameters by fitting, then you have to have a lot of experimental data, and the whole thing is trying to make sure the quality of the data is right and the real error bars in the data and stuff, so you can really believe what your fits are right. They call it the targets that you're trying to fit to. And you can look up, I suggest you go on the Brime website, you can see all about it, it's a nice story. So here they show how the GREMAC recommended this rate coefficient for OH plus formaldehyde, but then recently there's been some more measurements since the time of GREMAC, and the prime now recommends this red line here. And then they have an error bar on that parameter. And anywhere in this range would fit all the data, all the data for anything to do with methane and formaldehyde and H atoms, everything. That all the data that they can get their hands on are all fit by things, as long as you keep it in this range. But they don't know exactly where in this range it really is. And so then several groups tried to help them out by systematically making lots of measurements. And so, for example, the Hansen group started measuring multi-species time histories. So they would try to measure, during an oxidation reaction, many, many different species at the same time. And that gives you a lot of additional targets to constrain your fits, because you have to reproduce a lot of observables simultaneously. And then you can do comparisons. So this is measurements by the Hansen group at Stanford for these several different species, and then they plugged in somebody's model, a dryer model, and compared. And then this is great for like identifying where there's a weakness in the model, where it's not quite consistent with the data, and then you can go back and try to figure out which parameters in the model would affect the predictions in this range, and then you can try to see how they would have to be varied, and then can you vary them without screwing up all the other predictions of all the other species. And the whole thing's automated. They have a computer program that just, every time you touch a parameter, it repredicts everything, all known data, and then tells you, have you screwed up the fit with something, the prediction of something or other. And so it says, no, you're not allowed to vary that because you're going to break this other thing. All right, and then this, let's go over this for a minute. And recently, Tarani's been trying to do this, but a little bit less ambitiously, to try to go to simpler array systems and really firmly understand the correlations between all the rate parameters. So in the GRI MEC one, you had so many parameters, there's 325 parameters, that it's hard. You can't see it as a human what the correlations are. You can compute the correlation matrices between the 325 parameters. You just get this gigantic matrix, lots of off-diagonal elements. And it's like a little bit hard to understand what's going on. So Tarani, to back up, let's do it for a simple case where I only have a couple of reactions. And so that's what this is. So he just went back to H+O2. In this case, there were direct measurements for the different reactions and different temperature ranges, and also there's a bunch of ignition time direct measurements which are very sensitive to these reactions. And so you try to find, are there values of the rate coefficients which reproduce all, 30 experimental measurements correctly with these two parameters, the two rate coefficients. And then you could find what the correlation matrix is. And it turns out that the two rate coefficients are really highly correlated, correlations like 0.8, except at some little spot here at this temperature range, you can start to determine them separately. But otherwise, you really only can determine some linear combination of the two. And this is the general problem with a multi-parameter fit. And this is actually hidden inside the GRI MEC in the prime, is that they find a parameter range that works, but there's no guarantee for sure that that's the best parameter. And then they have a way to try to represent the correlation between all these parameters, but it's a little bit hard to see it just because it's so complicated. Here it's like kind of very simple. You can just see the one off-diagonal element has a big number. All right, so all that stuff is like trying to treat it as a giant fitting problem of determining the parameters. But since the quantum chemistry is available, you can turn it around and do it a totally different way. You can say, I'm going to predict everything with quantum chemistry, and I'm not going to fit anything. That would be the extreme opposite point of view. Okay, and so what people do right now is actually a combination. So people have done a lot of work on the small molecules, and they did a lot of experiments, and they did a lot of least squares fitting, and they determined a bunch of the rate parameters pretty accurately by doing that. And so those ones most people take and say, okay, that's the truth. We'll use those numbers. And then but I need a lot more numbers when I want to predict my new fuel. So I want to predict JP10, for example. This is fuel my group just worked on. I have like no rate constants of JP10 that anybody knows. Maybe the thermochemistry is just known. That might be about it. And so for that one, I need to estimate somehow zillions of reactions of all the JP10, but eventually the JP10 falls apart down to methyl radicals and H atoms and stuff like that, and then I can use the rate constants that are really well known. So the way that usually do is people start from the best small molecule mechanism you can get your hands on, and then you just start writing down reactions of all the other reactions that you think are going to be important in your system. And you estimate all the new reactions and all the new species parameters as best you can using usually group contribution methods because it's easy. And then if you're willing to spend more time, you'll do quantum chemistry calculations to try to nail it down. And then if you eventually decide that some reaction really matters a lot to you, then you might try to do an experiment or persuade somebody else to do an experiment to measure that particular parameter for you. So that's kind of this is now the mainstream method of doing it. But there's two different outcomes. So people who are trying to make a model because they want to predict something for a design problem. Suppose you're going to use JP10 in your jet engine, and you want to be able to predict, say it's relight. So you want to know the ignition delay under certain conditions for relight conditions. Is it going to ignite again or not? And so that's all you care about. You don't care about what molecules of JP10 it makes. You don't care about the intermediates. You don't care about the emissions. You don't care about any of that stuff. All you care about is it going to relight or not. So all you want is a model that predicts, given some inputs, what's the ignition time. And if you can do that, then you're happy. So in that case, when you do this, when you make this model the first time for JP10, and you make all your estimates, and then you predict the ignition time, and you compare it to experiment, it's not going to be right. There's no way your prediction is going to exactly match the experimental time, because the experiment has an error bar, and your model prediction has a much bigger error bar. So what often will be done is a person will just tune a parameter in the model and force it to exactly match the ignition delay that they care about, and then hope that the model is physical enough that it catches the dependence of how the ignition delay changes with some minor tweaks. And so you can use it as a predictive model to predict the ignition delay, even though if you think about it, you just took some parameter that you had your best physical estimate and you just randomly just tweaked it to make it force a fit. And this is actually the mainstream approach, because most of the people doing this, they're not chemists. They don't care about really if it's exactly right about the rate coefficients. They want to have a model that predicts the thing, the phenomenon that matters for them in their engine or whatever they're trying to predict. And so if it doesn't predict that accurately, it's of no use to them anyway. So they adjust it. So that's the most common thing. It's easy to tell if this was what someone did in a paper, because all you do is you look at their plot that has a comparison of the model prediction and the data. They always have a plot like that. If the predictions go through the data, that means they did this. Okay? Because there's no way that if you consider all the uncertainties and you have all these parameters are uncertain, there's no way that you're going to predict things that accurately. If the predictions don't go through the data, then they might have been this other approach. The other approach is you just believe your predictions and you use the model to show how bad you are. Right? The model is trying to validate, to try to check, figure out what the error bar is by compared to experiment. So this is the second approach. Now, I'm a big advocate for the second approach, because I think that in the end, we really want to be able to predict stuff. And so I'm really interested in knowing how far off my predictions are from the truth. And so that's my approach. But of course, a guy who's trying to make an engine doesn't care. They're not in the business of trying to make predictions. They're in the business of actually having a model that predicts their fuel and their engine. And they just want to tweak the model as appropriate to make it match close enough that they can use it for their design work. So there's a huge philosophical divide here. So this is an example. This is a model from the group at Galway. A guy named Henry Couron is the leader of this group, and he's a very famous model builder. And he's one of the adjusted school of model builders. So he says, people need to have natural gas models because people are getting a lot of natural gas. And so he started to build a model, used group contribution methods for most of the numbers. If there was experimental numbers, he used those. Once in a while, there's a quantum chemistry number, he used that too. And he wrote down what he thought were the reactions are probably important. And then he predicted all kinds of properties like the flame speed of natural gas, the ignition delay of natural gas, other things you might want to know. And then he compared those to experiment. And if the deviations were too big, then he went in the model and just adjusted a few parameters to make it match them all. Okay, and so this is a nice model. Now, I should comment that when you do this, these models have like maybe 1,000 rate coefficients in them. When you build one for such a big mixture, you're going to have a lot of rate coefficients. And he'll probably adjust maybe 3 of them in order to force the fits, because he doesn't have that much data on mixtures like this. So 3 of the parameters of the 1,000 parameters were adjusted. All the rest of them are your best estimates going in. And if you read his paper, he'll tell you which 3 he adjusted, so you know. And you wonder, where the heck did he get all these parameters? So here's an example. For this reaction, this is a dimethyl ether peroxy radical. It's very important how it isomerizes to the hydroperoxide, because this is going to eventually lead to release of OH radicals. And in this one, if you look inside his code, he says the way I compute this is I say that the EA is equal to the heat of reaction of this endothermic reaction plus a number for the ring strain correction plus the typical barrier height for an H abstraction, which I use this formula for, which has to do with the heat of reaction for the H abstraction. And so that algebraic formula is how he estimates this EA. So all he needs to know is the thermochemistry to make the estimate of the EA. So that's great. But again, who knows if that number is really how close it is to the truth of the real rate coefficient, or the real EA for this reaction. But it's a reasonable number. These correlations came from somewhere, so they're not ridiculous. So it's somewhere within a few kcals probably of the real EA. And it's good enough that he can write down a model that's like semi-quantitative. So he has something that's sort of sensible to do it. And then it won't quite fit, so then he'll go back and just adjust one of the parameters to make it fit. And so there's a paper here that has estimation rules, how to estimate different kinds of reactions if you know the thermochemistry of the reaction. All right, so there's a lot of issues that come up right away when you think about this. So the first one is, where did we figure out which species and which reactions I should include in the model? I can't include them all because there's too many. If you think of all the possible reactions in the world and all the possible species in the world, it's like infinite. Well, maybe not infinite, but really big, like 10 to the 23rd, kind of big. And so I'm not going to put them all in my model. So somehow somebody decided which ones are going to be included in the mechanism. And what you would like is that all of the ones are included that are important and not too many that are not important are included. Because otherwise I'm just adding extra species in and just clogging up my mechanism with stupid stuff that's not relevant. And so this whole question is the question of mechanism completeness. Is my mechanism complete? If I left out an important reaction or important species, then I would expect that my model would not fit the data if it was really important. And if then I tried to force the model to fit the data by tweaking parameters, I would end up tweaking to really unphysical things because I'm covering for the missing reaction or missing species by tweaking some other parameters, which is can be really bad actually. So this is a very important question. Have I achieved mechanism completeness? How can I test if I have? Another important thing is mechanism reduction. So at the end of this day here, I might end up with a model that has, did we say how many species are in his model here? No, it doesn't say, but it's a lot. It's like more than 1,000 reactions, maybe 300 species or something. And so if I go to my CFD buddy and I say, can you please predict how the natural gas is going to burn in your gas turbine combustor, turbulent flow, and here's my mechanism. I think it's really great. And then he says, how many species you got? You say, well, I got 350 species. I got 1,200 reactions. I'll say, OK, you get somebody else to do it for you. Right? Because his code can only handle 20 species and 100 reactions. And he's not going to modify the whole code to try to deal with your goofball mechanism with 350 species in it. So that leads to the whole question of mechanism reduction. Is there some way to try to write a simplified set of reactions and species that captures what's important for the phenomenon you care about? Now, the key there is you have to know what phenomenon is important to you. Because, of course, if all the species, suppose the model is perfect, it's true, all the species are really there. They're all really reacting according to all those reactions. And if your important observable was the concentration of one of those species, you better not cross that species out, right? So for example, suppose you care NOx emissions from your gas burner, which you might well do, then you better not cancel NOx out, even though NOx is a very low concentration species. And in fact, you better not cancel anything that's on the pathway leading to NOx. Otherwise, you're not going to get the right prediction, right? Because you threw it away. So model reduction is very tied to which observables you care about and how accurately you care about them. So a lot of times you care about heat release rate, but do you care about it to 10% accuracy or 1% accuracy? If you only want 10% accuracy, it might be pretty easy. If you want 1% accuracy, I might have to leave a lot of detail in my chemical mechanism to capture that. So you have to know what you really care about and how much you care. And there's a trade-off between you're making the computation easier by getting rid of species and getting rid of reactions, but you're losing accuracy too, so you have to figure out how much you're willing to trade off. And so there's a line of research is about model reduction that's quantifying that trade-off. How much speed up do you get in your calculation for how much fidelity you lost in the chemical mechanism. And there's a general idea too that when you do the CFD, normally you make some trade-offs to try to reduce the computational cost as well in the fluid mechanics calculation. For example, by how you choose your mesh. You might choose a coarser and coarser just to make it easier for you to do the calculation. And so in the sort of a conceptual way, you like the error that's due to the CFD and the error that's due to the chemistry, neglecting some of the chemistry, should be sort of comparable orders of magnitude, right? That would be sort of the optimum way to do it. So trying to figure out how to do that is, I would say, a research topic people are still working on. All right, then the next issue is once you've listed all the species and reactions you're going to put in your model, is how you're going to estimate all the thermochemistry and the rate coefficients for all these things. And there's numerous issues with this. So we talked a lot about how people calculated the rate coefficients, how people calculate thermochemistry. There's a lot of subtlety about exactly how you do it, and people have slightly different approximations for doing it. They have different libraries of the known reactions. There's still disputes about what the numbers are for some of them. So somebody who took somebody's library and somebody else's library, they might actually have different numbers for some of the rate coefficients. But in general, what everybody wants to do is what's called sequential refinement. So you want to say, well, I have 1,200 reactions, but when I do sensitivity analysis, I find that the thing I care about is only sensitive to 7 of the reactions. And so I want to put all my effort in trying to get those 7 rate coefficients really accurate and not worry about the other 993 reactions, because they're not going to really matter. And then finally is the question of uncertainty propagation. So ideally, you'd like to run the CFD burner simulation, and at the end, it would say your NOx yield is going to be 20 parts per million plus or minus 7 parts per million. Now, right now, maybe you can get the 20 parts per million number, but usually most people wouldn't have any way to figure out what the error bar is on the prediction. So trying to figure out how to propagate the uncertainties in the rate coefficients and the thermochemistry through, all the way through the whole CFD simulation and finally get error bars in the final prediction, that would be very valuable. And if you found out you were 20 plus or minus 100, then your boss might be a little concerned about running this burner. And if you found out you were 20 plus or minus 7, he might be really happy. And so it'd be good to figure out, how good do we have to be to achieve that 7. So this leads to a whole discussion about what are sensitivities. And what we usually do in kinetics are the first order sensitivities. What we do is we compute the coefficients d logarithm of the concentration of species I at time tn, d the logarithm of the A factor of reaction J. These numbers are called the normalized sensitivity coefficients, like Sij of Tn. And many of the softwares, like Chemkin, can automatically compute these for you. So when they solve the simulation predicts all the species as a function of t at some time points. That's what you get as the output. The main output of a Chemkin type simulation is what all the concentrations are as a function of time. If you're doing a CFD, you also get as a function of space as well at the different mesh points. And then you can also get it to give you these S's, which are how sensitive is that prediction to the A factor of reaction J, to the Arrhenius A factor of reaction J. And so those are really nice to look at. And what you would look for is try to find the ones where this is really big. So if you have, actually any of these S's are sort of 1 or bigger, that means you're pretty sensitive to the A factor. So that means if you increase the A factor by a factor of 10, you'll increase your concentration by a factor of 10. A lot of times, most of the sensitivities are like 0.1. So that means if you increase logarithm, say increase A by a factor of E, so by a factor of 3, then you change the concentration by like a 10th, something like that, if I did that correctly in my head. And so then you don't have to worry about it so much. So when you look at it, when you do these sensitivities, what you'll see is there'll be a couple of them that'll be big, like bigger than 1. And then you'll have many, many, many that are really tiny, 0.1 and less. And so a lot of times people will say, well, I don't worry about all the small ones, and I'll just focus on the reactions that give me the big ones. But this is for the concentrations, but of course for a real device, a lot of times you don't care really about the concentrations of most of the species. So this is not really what you want. You might want the ignition delay. You might want the flame speed. So there's different observables you want. But these guys, usually you can write these as a function of the C's. Sometimes it takes a little effort to figure out how to write this. But if you have the concentrations everywhere, you should be able to figure out all these derived quantities from it. And then you can do, if you have these derivatives, these are really, this is equal to dCi dAj times Aj over Ci. So you have the derivatives. If you have all these derivatives, then you can also figure out things like the derivative d tau dAj is some function of these guys by chain rule. So then you can get the sensitivity to everything you want to know. Now the AJs are, most of the parameters in your model are the rate coefficients, but they're not the only ones. And it's very important to also do sensitivities to the thermochemistry. So another really good one to do is d logarithm of Ci, d the enthalpy of species K, or L. There we go, species L. So this is a different kind of sensitivity. It's how it's sensitive to thermochemistry. And that way you can figure out if there's some enthalpy. Because many of these species, you're estimating the enthalpies with group contribution methods. They could have pretty big errors. You want to know which of those are ones you really need to worry about. And then finally, another one that's good to do is d ln Ci t d ln Cj of t naught. So sensitive to the initial conditions or to the boundary conditions. So a lot of experiments, the boundary conditions are not as perfect as you think they might be. And you're not really sure what, you have an idealized picture of your experiment. You think the temperature at the inlet is exactly whatever it is. But in reality, the temperature could be off by 5 degrees or something at the inlet. That propagates through and causes everything to be different. So understanding that is very important. And in fact, at the GRI MEC, a lot of what they discovered was the biggest uncertainties were actually uncertainties due to the fact that they didn't know the real boundary conditions in the experiments, and that really screwed up a lot of the attempts to try to backfit what they're doing. All right. Let's see what we got here. So this was this is a paper pretty recently by Burke, and he's trying to understand how the combustion behavior depends on all the parameters in the theoretical calculations. So not just to the experiments. So these parameters, this d ln Aj, this really works great when you have a simple Arrhenius form. But suppose you have one of those pressure-dependent reactions, K of Tp, like a TROA form or something. Then the whole thing is more complicated. So, I mean, just for Arrhenius, you'd already have, in principle, there's another sensitivity that's d ln of concentration I at Tn d the Ea of reaction J, right? This could have a different, if you have something that's a non-isothermal system, then this T dependence of the rate coefficient could be very important. The fact that it reacts faster here than it does here, maybe that gives you a gradient, for example. It might affect the flows and stuff like that. So this is another parameter that you might need to know. And in the cases where you have those chemically activated well-skipping reactions we were talking about last time, so if you have one, so you have a case like this, A plus B goes to C, goes to D plus E. You might be sensitive to this quantum mechanically calculated barrier height. That might affect the rate for A plus B goes to C, D plus E, and also the rate for A plus B goes to C. And so then what you should do, if you find you're sensitive to this, is actually go back and recompute this with a higher level method to try to narrow the error bar. So Burke has written the sensitivity analyses to do that, including all the inputs to the quantum mechanical calculation. If you know, the rate calculations were complicated. They had some steps from the second derivative matrix, some other stuff from the V's at different points, all these different things contribute. And so if you knew which of those you were sensitive to, then you would know what to do to try to improve the calculations and which steps are the most important. So that's what this is about.
I know that's going to be a specific thing for any given problem, but using the RMG tool, if you were to use one of the more accurate solvers that you have in it, do you think that would reduce the amount of error that you're putting into your model?
Let's see if I say it this way. What we have done before is we did the sensitivity the normal way. We found out we were sensitive to a reaction where the number came from a quantum calculation. We went back and did the quantum calculation with the higher level method. Therefore, got presumably a more accurate rate coefficient, put that one in, and all of a sudden the model predictions are now closer to the truth. Okay. So sometimes it works out. I don't know. It would be nice to have that all automated. So it would just automatically, at the end of the job, it would go back and spawn quantum chemistry calculations for all the numbers that should be improved. Or maybe you automatically send an email to Ron Hansen, please measure this reaction for me. That's actually the prime guys are doing that. They were like making little automatic emails you could sign up to get notified if, you know, which reactions need help. You could write your next grant proposal to measure this reaction because the prime guys have told you that this is the most important one to measure. Yeah?
I have a question regarding Tuesday's lecture.
Yeah.
You talked about tunneling through
Yep.
potential barriers. When you're dealing with a detailed mechanism, do you have any idea what reactions maybe would experience tunneling through these potential barriers?
Yeah, so when we write down the expression for KFT, if you compute it, normally you would try to put a tunneling correction in the computation. So the KFT ends up with normally an A t to the n, like this type thing. And this n often is sensitive to what you computed as the tunneling. If you did experiments at a lot of temperatures, especially in the low temperature region, you would also pick it up that way. How accurate it is, I don't know, but at least there's some attempt to have it in there. And again, if you did a sensitivity analysis and found you're very sensitive to this rate coefficient, that'd be the kind of thing where then you might want to call up Don Trular and say, hey, can you do some really fancy multi-dimensional tunneling method and try to get this rate more accurately for me or something like that. And in fact, so Don Trular and I were on the same center. It's actually funny, in the summer school. And I did that several times where you know, the model, the sensitivity analysis said we were sensitive to some particular type of reaction. And I would call them up, send an email with, you know, here's 6 reactions that come up high in my sensitivity analysis. You know, I'll do reaction 1 and 2. Can you do reactions 3, 4, 5, and 6 at higher levels? And so that's what the students did, and that was very helpful to try to narrow it down what the problems were. It doesn't always work. You know, sometimes you recompute the reaction with a higher level of theory, and you get basically the same number you had before, and so it didn't really improve your agreement. But at least it's a reasonable thing to try. I guess I should also warn you. So you get these things. These sensitivities are really nice, easy to get. You should always do it. But these are first order sensitivities. So really there's like a Taylor expansion that the concentration species I Tn, or say logarithms, is equal to my nominal value. That's using my nominal values of the rate coefficients plus d ln Ci d ln Aj times my error in ln Aj plus like it's a Taylor expansion, And so if I only use this first order sensitivity coefficient here to try to figure out what to work on, I'm not picking up this effect at all. It's like I'm assuming it's 0. But sometimes you get cases where these are big, the second order sensitivities. And also, this is only evaluated at C nominal. It's like it's evaluated for my current estimate of the concentrations. So if my model is too bad, my estimate of the concentrations might be way off from reality. And I might be evaluating this at the wrong place. And this thing might have a dependence that in the range where I calculate it, maybe it has a very small number at my C nominal, but at the true value of C, it would actually have a big number. And if it's a small number, I say it's not important. I may never look at that reaction again, even though I should have. So this is like a kind of tricky thing about how to refine models. And it's the farther you are from the truth, the harder it is to figure out what to do. And as you hone in on the reality, you start understanding all the major effects are in there, all the major reactions and species are in there. You have pretty good numbers for all of them. And then then you can really be pretty confident about what's going on. But when you first start, like I started working at JP10, that's like 6 years ago. I had no idea. And it's only this spring I'm finally getting ready to write a paper. We finally gone through and found all kinds of reactions that we didn't think were important turned out to be important, and some we had misestimates of a few thermochemistry and stuff like that. So this currently is not. It's a project. It's not a just press the button thing. But in principle, it could be. It's not. I mean, everything we're doing is like following a systematic procedure to do it. What else? Oh yeah, this is about the Burke. What do I do with the Burke guy? Here we go. So Burke's idea here to try to vary these parameters is very helpful for extrapolation. So if I want to predict D plus E, so I'm trying to predict the K of TP for A plus B goes to D plus E. If I only care about it at one temperature and pressure, I could just vary the A factor, just adjust the A factor and make it fit. But if I want to predict the whole dependence at all T's and P's, I really need to use a model for the potential that's actually accurate so that I'll actually predict accurately the fraction of how much is going to go to D plus E compared to how much is going to go to C. You sort of those curvature, the knees in the plots that we did yesterday on the board. As the non-Arrhenius plots, they come up and they cut over somewhere. If I want to get that cut point correct, at what temperature does it cut off, at what pressure, I really need to have the shape correct of these things. And so identifying which part of the potential is controlling, making sure that part of the potential is really as accurate as possible is beneficial, not so much for the exact condition I'm at, but for like predicting other conditions. Because then I'll be like physically correct. So the extrapolations will be better. There's another nice paper by Tomlin in the last combustion symposium. And it's all about, again, how to do the sensitivity analysis. And also there's other kinds of uncertainty analysis. So this is an interesting thing. So if you use Chemkin, for example, you can get these kind of plots, which are how sensitive different observables are to different reactions. So in this case, for example, the white bars are the flame speed and the gray bars are the ignition delay. And you can see that they're both sensitive to H plus O2, though with different signs. But this reaction here, which one is it? OH plus methyl, that only affects the ignition delay. And this reaction here, OH plus CO, mostly affects the flame speed. You see that kind of stuff? So this is interesting things to learn from the local sensitivity analysis, similar to what I just wrote there, first order sensitivity analysis. You can also say, boy, I'm really worried my model is completely crazy. I might be way off. And then there's a procedure called global sensitivity analysis that just varies things wildly. So if you think when I write this Taylor expansion here, this is convergent if these guys are small enough. But if these are really big, then the square terms might be bigger than the first order terms, right? So if I think I might be way off, then doing this Taylor expansion is kind of a dumb idea because it's not going to be convergent. And so there's other procedures you can do to try to see how a gigantic variation, a gigantic error in one of the A's, for example, might affect things. And so that's these global sensitivity methods. And one of them is called Morse analysis. And if you want to read it, you should read about that in our paper. But it was able to identify that the thermochemistry of this species turns out to be like really, really important for predicting the ignition delay. And that didn't come out so clearly in the local sensitivity analysis. All right, I think we'll stop right now. And then afterwards, I'll tell you about how my group does this.